All right, thank you for not running away during the break. So just before the break, we stopped at roughly this point, right? The capacity is 1 minus p. And now let's look at the other extreme, the sort of Hamming view, the fully adversarial channels, where the adversary is like super strong, sort of. And as I alluded to before the break, things are really quite different over there. So the adversarial channel, you can model it as the previous one, right? You have y is equal to x if s is 0, y is an erasure if s is 1, and we'll put, just to make it behave sort of like the random channel. So to have something like an apples to apples comparison, we'll also put a constraint on the adversary, that is the number of ones should be less than p times n, right? And this is only fair because in the random channel, in expectation, the number of ones in the which are erased is roughly p times n, right? So this allows for some level of comparison over here. Okay, so now you could imagine having the same notions of probability of error, average and maximum probabilities of error, and with the constraint that the Hamming weight is at most n times p. So geometrically what would be happening would be, now if you demand a maximum probability of error, so again using the balls metaphor, though realistically the graph metaphor for the erasure channel is more directly relevant, but the balls metaphor would say that if I transmit this code word, there should be no overlap between the received sequences for this code word with any other transmitted code word, right? Because if there's any overlap at all, under a maximum probability of error metric, that would be immediately a probability of error, because if there's any overlap at all between even a single pair of code words, right, between the received code words for this transmitted code word and the received code words for this transmitted code words, then for this transmission, the adversary would always try to push it towards this received vector, and then the receiver would have no way of trying to distinguish between these two, right? So maximum probability of error in an adversarial setting is a much more stringent requirement, right, than a maximum probability of error in the Shannon setting, right? You do not allow any overlap at all. And similarly, the average error under the Hamming view is also somewhat different. So average error would say, if the number of balls where there's any overlap at all should not be very large, right? So over here there's some overlap, over here there's some overlap. So you really, this is a bad transmission. Any one of these three is a bad transmission. This can be confused with this can be confused with this, right? So and so on. So really the only good transmissions are, in this case, this one and this one. These cannot be confused with anything else, right? Those are the only ones in this case. So this is actually a bad picture to show a small average probability of error, but really this would be the notion of average probability of error metric under a Hamming, like under an adversarial point of view. And again, you can do the same thing with graphs. So so graphically, for an erasure channel, you would want that all the possible received sequences for a particular transmission should have no overlap at all under a maximum probability of error metric, with all the sequences for another code word and so on, right? No overlap allowed. Okay. Yes. Okay, yeah, that's a slightly subtle point. Usually in the information theory community, our metric is to get a probability of error that is a decaying function of the block length. So that would not work. Yeah. Good. But actually, just to, I'm sorry, I was supposed to repeat questions. So the question was, what if, well, if there's an overlap between two, then I could guess correctly with a probability of half. And the problem is that we can't get a decaying probability of error. It's tied to one of the things we'll be talking about hopefully in this hour, maybe a little bit in the next hour, to do with a notion called list decoding, which would be a relaxed notion of decoding. Instead of decoding the truly transmitted message, you're allowed to decode a small list of possible messages, and if your small list does always contain the truly transmitted message, you'll declare success. and that is relevant to your question, and that does substantially increase the capacity as well. It will also be a very useful metric to look at. Okay. Now, again, just like in the Shannon view, over here we would also like to prove our converses under an average probability of error metric, which would imply a converse under a maximum probability of error metric, right? And we would like to prove achievabilities under maximum error, rather, which would imply achievabilities under average errors, right? Because direct arguments would give you those. We will not always be able to do it, but this is the desiderata. This is what we would like to be able to do. Okay. Now, interestingly, just like in the Shannon view, even in the Hamming view, at least in the omniscient Hamming view, the achievability under average error implies achievability under maximum error. Okay, so it really does say that just like the average versus maximum probability of error metric, really the capacity is the same. The same will be true even for at least for the truly omniscient model where the adversary knows everything. Even here, the capacities will be the same. Now, it's a little bit weird because it turns out we don't actually know the capacity in the omniscient model. We do not know the capacity of the Hamming point of view. We'll talk shortly about the fact that there's an inner bound, there's an outer bound, but we don't really have the actual curve. But no matter what the curve is the same for both these error metrics. Okay, and that's what the point of this slide is. It's a simple argument, so let's begin to get into it. Okay, so suppose someone gives you a good code, a code which has a certain rate, which has 2 to the nr code words under an average probability of error metric. Okay, and the probability of error is small. It's at most epsilon. Okay, so what that must mean is there's at most an epsilon fraction, so epsilon times 2 to the nr code words which have some overlap property, right? So you just expurgate. You throw these code words away. Right? Now your code book has shrunk now from 2 to the nr to something like 1 minus epsilon times 2 to the nr, right? Or if you want to be super careful, then, well, okay, basically 1 minus epsilon times 2 to the nr. But the rate is still basically the same, right? Because you take the logarithm of this, divide by n, in the exponent it's still really r plus some lower order terms which asymptotically go to 0, right? So this is basically saying that actually it's also a robust notion of capacity over here, right? Average versus maximum doesn't really matter. It's the same capacity that you have to worry about. Okay? All right. So yes, it's a very general argument. It does not work in certain ABC settings. Over here, over here okay, it gets subtle, so let me not get into it, but there are certain ABC models where you leverage the fact that the average probability of error depends subtly on the adversary's lack of knowledge, and therefore you can get an average probability of error, but you cannot get the same rate with the maximum probability of error. Okay, so it's a little bit subtle. Okay, let me repeat that question again. I'm sorry. So the question was, just because this is being recorded, so would this phenomenon show up even if there's no adversary? And certainly in the Shannon view it does show up, but in certain subtle adversarial models one has to be a bit more careful. Okay. So now let's begin as a warm-up exercise with something which again hopefully many of you have studied in a coding theory class. And I'm going to use the words information theory and coding theory in a maybe somewhat idiosyncratic manner, which not everyone always uses in this manner. So when I say information theory, mentally I will be thinking of something where the noise is random, right? That's often what we study in a first level information theory class. When I say coding theory, I'll be thinking of models where there's an adversary, where there's worst case noise and so on. And again, this is idiosyncratic. Often when people say coding theory, they often mean code design for information theory problems, for random noise channels, right? But I'll just be, when I say coding theory, I'll be talking about these worst case channel noise models, okay? Because that's also terminology often used in the literature. So in a coding theory class, one of the first bounds that you would often look at would be the so-called Hamming bound, which is a upper bound on the rate of a channel. Okay, and notice that this Hamming bound is plotted specifically for the binary erasure channel. So let me just describe it, because as several of you pointed out, the slides are not terribly clear, at least in this particular setting, for which I apologize. So remember, the capacity of the binary erasure channel was 1 minus p, right? And it will turn out that even the simple Hamming bound, which we'll prove in the next slide or two, will show that the capacity for the adversarial binary erasure channel cannot be 1 minus p. It has to be substantially less than it, like this. In fact, we'll prove something even tighter than this shortly afterwards. But at least it cannot be larger than 1 minus h of p over 2. Okay, so something like that is what we'll prove. H is the binary entropy function. We'll prove it's no larger than something like this. Okay, so the adversary, like having an adversary, has a dramatic impact. How do we prove this? So we prove it by saying, okay, so given any binary code with a minimum distance requirement of at least np, that is to say, every pair of code words should differ in at least np locations. Ones should be 0, 0 should be 1s, right? The Hamming distance should be at least np. Then the size of this code cannot be larger than something like this. Okay, it's a fairly simple argument, which again many of you have seen, but it's the first argument, so we ease our way into analysis, right? So let's do this. So it's basically a sphere packing argument. It basically says that the image that you should keep in mind is something like this image over here, where if you transmit a code word, the set of received sequences can only be within a certain Hamming ball. If you transmit this, the received sequences can only be within this, and they're not allowed to overlap at all, right? Because we just argued that average error and maximum error have the same capacity. We don't know what the capacities are, but they have the same capacity. So we may as well work with this image over here and argue that the received sequences for any pair cannot overlap at all. Okay, so if they cannot overlap at all, then it must be the case that every pair of sequences has to differ in at least pn locations, right? Because if there's a pair of sequences which differs in less than pn locations, the adversary can always erase those specific locations, because the adversary can erase pn locations, and then the decoder would be confused between these two different things, right? So it must be the case that every pair of sequences has to differ in at least pn locations, right? Even in this erasure channel model. So so now what will we do? We'll say we'll try to pack, and this is not legible at all, I'll repeat this, but we'll try to argue that no matter what you do, if every pair of code words has to differ in at least np locations, their Hamming distance has to be at least np, then it must be the case that you can pack Hamming balls of radius np by 2. I mean, forget the quantization, like the half or something that you don't have to worry about, but basically there are Hamming balls of radius np over 2 that you must be able to pack into this space, right? And you must be able to pack 2 to the nr Hamming balls of this radius in there. So when you do this, then the union of all these Hamming balls cannot be more than the size of the space, cannot be more than 2 to the n, right? But the volume of each of the Hamming balls, what's the volume of the Hamming ball? It's the number of sequences which differ in at most np over 2 locations from the center of the code word, from the center of the ball, from the transmitted code word, is at most summation of I goes from 1 through np over 2 n choose I, right? N choose I is the number of locations, is the number of sequences which differ in I locations from a transmitted code word. Sum up I going from 0 up till the number of possible erasures, right? Not erasures, up to np over 2, right? And this quantity is going to be bounded from above, because the largest term is going to be the last term, so it's going to be the largest term is going to be n choose np over 2, and then just take a loose union bounded by np, something linear in n. So you have something like this. Use Stirling's approximation on n factorial, right, and do some algebra, and it basically tells you that the size of the code is, ignoring lower order terms, no larger than 1 minus hp over 2. Okay. and some dot notation. So basically we'll sort of ignore lower order terms like logarithmic terms and so on and exponent. Okay. All right. So that gives us an upper bound. Now a tighter bound is the Plotkin bound, which also will use the Hamming bound tends to be quite loose, and actually in most application or most theorems that we have tried to prove, it's not really that useful. But the Plotkin bound is truly useful. In at least a couple of recent works, we found it very useful. And it's also quite simple, so some of you may not have seen it. It's not always covered in coding theory classes, so let me repeat this. So what does the Plotkin bound tell us for this specific problem, but actually in greater generality as well? The Plotkin bound says that if you demand so remember, the Hamming bound basically gave a bound on the rate of the code as no larger than 1 minus HP over 2 for the adversarial erasure problem. The Plotkin bound will tell us that actually for any p larger than a half, as long as the adversary can erase more than half the locations, no positive rate is possible. Okay, this is a little bit subtle. When we dive into it in the next few slides, it's not that you can't choose any code words which have minimum distance at least n over 2. You can indeed choose a few, but you can't choose too many. You can certainly not choose an exponential number. In fact, it will turn out you can't choose even more than a constant number. Okay, so in that sense, it's a little bit subtle. You can have a few, but not too many. Okay. All right. So how does one prove this? And the technique is interesting. There's at least a couple of different techniques, one of which is different and is also useful. It's based on Cauchy-Schwarz inequality and so on. But right now, let me focus on a combinatorial way of proving this. It's via a so-called double counting argument. Again, quite straightforward, worth seeing. So this is going to be the quantity of interest that we'll look at. Okay. So think of your code. Think of all possible code words in your code, all possible x comma y code words in your code. Look at all pairs of code words, look at their Hamming distance and add it all up. Okay. So this quantity we'll bound in two different manners, compare with each other, and that will magically give us a upper bound on the size of the code. Okay. So so what do? We basically write all the code words as rows of a matrix. Okay. So this is the first code word, this is the second code word, and so on. So therefore this matrix has n columns. It has C rows. C is, let's say, the size of the code. So it has C rows, it has n columns. Okay. So now this summation over here, well, there are every pair of code words differs in at least d min locations, right? The minimum distance of the code is d min, let's say. So, or here in this slide it's d. So therefore dh comma y is at least d, and there are C choose 2 ways of choosing x and y, right? So therefore this quantity is at least larger than this quantity, and we multiply by 2 because we are taking into account the degeneracy between x comma y comma x. So there's that. Okay. All right. Now the other way of bounding this is to say, okay, now instead of doing row wise sums, we'll do column wise. We'll try to bound this quantity column wise. And what do? We say, okay, now this summation over here, it's basically, I'm looking at every pair of code words, right, and I'm looking at the number of locations in which they differ. Now in particular, that's just like saying I'm going to look at the first so look at the summation. The summation is just over all the coordinates of the code word. So first, for this pair of code words, I'm going to see, do they differ or not? Do they differ or not? Do they differ or not? I'm going to add them all up together, right? So they're going to differ. Okay. So instead of first adding up these differences and then adding up these differences and then adding up these differences, let me just focus on one column and say, do these differ or not? Do these differ or not? Do these differ or not? And so on. So just in the first column, let me see how many differences there are, add them up, then move to the next column, add up those differences and move to the next column and so on, right? So basically what will end up happening is you can break this up into a double summation and interchange the summations. That's all that's happening. Okay. So really what it comes down to is, in a single column, if there are, let's say, Si, in the ith column, if there are Si 1s, then there will be C minus Si 0s, right? So the number of pairwise differences will be Si times C minus Si, right? And then again, to take into account that degeneracy, you multiply by 2, right, and add up over n. So you end up with a bound like this on the whole summation. Okay. Yeah. So sorry, you end up with this. This is actually equality, right? And then you say, well, this quantity is maximized. This quantity is maximized when for every I, Si is C over 2, right? Because it's a quadratic in Si. So just, you know, basic algebra, differentiate, and then it's maximized when Si is C over 2, and therefore you have a bound like this. Okay. And then some basic algebra, compare these two quantities, and I'm not going to bore you with it, but basically it tells you that the size of the code is no larger than twice the minimum distance divided by 2 times the minimum distance minus n. And what does this imply really? So it implies that if the minimum distance is greater than n over 2, then it's not explicit over here, but you can do, for example, something like this. You can prove a bound like this, that if d is larger than n by 2 times 1 plus epsilon, then the size of the code is order 1 over epsilon. I think it's something like 2 over epsilon times 1 plus epsilon or something like that. It doesn't really matter. It's like order 1 over epsilon. Okay. So that gives us a pretty tight bound, right? It says that if you want to be even slightly larger than half the minimum distance away, then the size of your code is not very large at all. Okay. By the way, just to build some intuition into this, so think about pairs of code words. So if you wanted to choose just 2 code words, it's very easy to get much larger than n over 2, right? You could choose one sequence with all ones, one sequence with all zeros, and the minimum distance is n, right? Oh, so what's the problem? Well, now try to choose another code word. What do? Well, it starts getting trickier, right? So if you want to choose 3 code words, then maybe one way of doing it is to choose 2n by 3 ones over here, 2n by 3 ones over here, and then 2n by 3 ones in this manner, right? Something like this, right? So then you can get 3 code words with a distance like this, and actually you can put in a 4th code word with all zeros over here, So now every pair is going to differ in 2n by 3 locations, right? So okay, so you can still get substantially larger than n by 2, but actually this is it. So you can't get more than 4 code words with minimum distance 2n by 3, right? And the combinatorics of this is quite interesting. It's been examined quite a lot. So for example, just as general knowledge, turns out if you want distance exactly n over 2, there are these things called Hadamard codes, which are related to the discrete Fourier transform. So you can get logarithmic number of code words at distance exactly n over 2, right? So it's like if you want substantially larger than n over 2, then it's a constant number. If you want exactly n over 2, you can get a logarithmic number, and as soon as you go below n over 2, you get an exponential number, right? So drastic change in the behavior of the whole thing, right? But this is what the Plotkin bound gives us. Okay. All right. So so this is the Plotkin bound. There are other bounds. So there's the so-called Elias-Basiligo bound. There's a first LP bound, second LP bound. The Elias-Basiligo bound can be viewed as a Plotkin bound plus a little bit more careful counting. The LP bounds are truly different. They're fascinating objects, and honestly, I don't have a good, clear exposition of them. I just have a mechanical exposition, so I'm not even going to try. There's a relatively recent paper, like around 10 years ago, where they analyzed the linear programming bounds in a fairly different manner using Fourier analytic techniques over the Boolean hypersphere. So that's really quite nice. But there's something quite non-trivial happening with the LP bound, which if you're at all interested in coding theory, I would encourage looking at. But anyway, all of these things overall tell you that the overall upper bound on the capacity is given by something like this blue curve over here, and then nothing is possible as long as p is greater than a half. Okay, so if this is how you want if this is the number of erasures you want to tolerate, or if this is the fractional minimum distance you want to tolerate, then you can't get better than the light blue curve and then the green line. Okay. All right. While we're on this Hamming part of the thing, it's also second LP bound, which sort of combines a few things, but basically, okay, so instead of the blue curve, there's some orange curve and so on. So while we're on this thing, so we talked about impossibility results. Let's also talk about a possibility result, about an achievability, and this brings us to the natural Gilbert-Warmup bound, which is actually quite similar to what we talked about in the Hamming bound, with one important difference, and that gives us something. Surprisingly, even though these were proved quite a long time ago, 52, 57, and the best converse, by the way, in the 70s by McLeish, Ramsey, Rodmich, and Welch, no improvement, essentially no improvement in the last 60 to 50 years, depending on how you're counting it, and so on, right? So it's a big open problem. It has connections to geometry. Any progress at all would be big news, right? So if you're looking for things to bang your head against the wall on for the rest of your careers, this is worth doing. Yeah. So there's a couple of proofs. Gilbert gave a greedy approach leading to nonlinear codes. Warmup gave a linear code which basically has the same rate. I actually forget which proof is coming up in these slides. So okay, let's look at Gilbert's greedy code. So over here, to get a code with minimum distance d, which is Pn, well, it's just a greedy approach. So start with an empty code book, choose any code word to begin with. Then now you have to exclude all binary vectors which are at Hamming distance np from you. So just exclude them, throw them away. Now choose another one, exclude them, throw them away, and so on. So just do it greedily, right? And it's basically the same argument as before. So except now the balls are of radii, instead of being of radii np, np over 2, they're of radius np, right? Because now you want to throw away all sequences at distance np, right? So as to ensure that you're not going to have an overlap. And now you're going to overcount. So even though you've already thrown away some sequences, the next time you throw away a sequence, you may be throwing away sequences you've already thrown away before, but you're just going to overcount, and then you'll say that how many balls can I pack in? So when you do this computation, when you basically say the minimum number of Hamming balls of radius np you can pack into a space of size 2 to the n is going to be 2 to the n divided by the volume of such a Hamming ball. Use Stirling's approximation, compute, and you get that it will turn out to be you'll get a rate of 1 minus hp. Okay, so okay, so that's 1 minus h of p. That's the Gilbert-Warmup bound for erasures. Keep in mind, by the way, that everything I've been saying has been focused on erasures. In the literature, often the focus is on bit flips, and there's a factor of 2, right? So for example, if you want to ensure that two code words are not confusable under bit flip errors, then you'd better ensure that the minimum distance is 2pn rather than pn, right? Because the adversary can change pn bits from this direction, pn from this direction, so that they meet in the middle. So there is a factor of 2 that you have to worry about over there. Okay, so just mentally keep this in mind. Okay, so yeah, this is the Gilbert's greedy approach, and well, just because it's also here and won't take too long, let's also talk about Warmup's linear code approach, which is revealing. So this will be slightly reminiscent of the very quick argument I gave before the break, talking about the random binary erasure channel, but now it will be for an adversarial binary erasure channel, and Warmup's construction sort of works somehow in a similar manner, but with some important differences. Okay, so yeah, so here's a fact. So given a non-zero message and a uniformly random matrix G, so if I look at any row of G, right, the dot product between M and G is uniformly distributed in 0 and 1, right? The dot product between M and the first row is 0 or 1 with probability half. The next dot product is still 0 or 1 with probability half and independent of the first row because of the independent randomness in the second row of G, and so on, right? So if you think about this, the vector corresponding to M times G is a uniformly random vector as long as the message is the non-zero message, right? And this fact will be quite useful in this proof. Okay, so yeah, so the code word is uniformly random. Okay, so so what do we do? So we'll want to argue that for any non-zero message, the probability that the encoding, the probability that the code word being transmitted has high Hamming weight, has Hamming weight larger than NP, yeah, we'll want to establish this fact. We'll want to argue that with high probability over the design of the matrix G, for every message, the Hamming weight of M dot G is larger than NP. Okay? And to do this, we'll use a probabilistic argument. So, well, what's the probability that a single transmitted code word has Hamming weight less than NP? Well, that's the probability that a single that a dot product has Hamming weight less than NP. But we just argued that this dot product is uniformly random. It's uniformly randomly distributed over the whole space. So that's just the volume of this ball divided by 2 to the n, and that, by the similar sort of Stirling approximation argument, is at most 2 to the minus n times 1 minus hp, right? So what that tells us is that if I now take a union bound over all the possible messages, the probability that there exists a message such that the corresponding code word has low Hamming weight is going to be small. It's going to be the size of the code times, there's a negative sign missing over here. It's going to be less than 2 to the nr times 2 to the minus n times r, whatever, right? And this will be minus 2 to the n epsilon. So this is basically saying, right now, this is just saying the following fact, that if I've chosen a random matrix G, the probability that there is even a single code word corresponding to a non-zero message which has low Hamming weight, which is Hamming weight less than NP, vanishes, goes to 0 as 2 to the minus NP, right? Okay, and that's really all we need, right? Because the minimum like the distance between the 0 and any other code word is therefore at least NP, which tells us, because of the linearity of the code, that all pairs of code words are at least distance NP apart, right? So here we're implicitly using the linearity of the code, okay? Now, this proof is clean and nice and so on. It's also remarkable that it's basically the best proof that's known despite the long gap. Some people, like, you know, whenever coding theorists get together in a room, they're like, do you believe Gilbert-Ashmore? Do you believe LP? And really, like, if you did a poll among coding theorists, more of them would, like, if they had to bet as to whether the LP bond is tight, the GV bond is tight, something in the middle is tight, I would say a plurality would bet on the GV bond being the right answer, without any proof, but it really seems like the right answer. Okay, it's a nice guess. Don't quote me on this is being recorded, isn't it? But okay, I'm just making a claim here based on my gossip. Okay, so take that with a pinch of salt. Okay, so. All right, so that gives us a lower bound that corresponds to this. And just to summarize, so therefore, here's what we know, right? Forget the Hamming bound, doesn't really matter. But we have a GV bound, that's this red curve, that's achievable. We have an upper bound, that's a LP bound, that's the tightest known, that's the converse. The Plotkin bound tells us that nothing is possible when P is greater than a half. And notice the vast difference between this and the corresponding capacity of the binary erasure channel, right? So having adversarial noise really has a big impact, okay? And something I think we don't have on these slides is actually, so if you remember, for the binary erasure channel, we actually even have computationally efficient codes getting to the capacity of 1 minus P, right? Whereas if you demand computational efficiency for the adversarial binary erasure channel, the best codes, you know, it's a complicated mess, but it's fair to say that really the best codes that we have that are computationally efficient, not even terribly computationally efficient, like something like order n to the, like some polynomial, some large degree polynomial, is not great. It's like substantially below this curve as well, okay? So, so there are all sorts of penalties when you want to operate against an adversary, okay? So that's something to keep in mind. Okay. So around 25 more minutes by my time here. Okay, we can do the following. I just trying to guess the sense of the room. I feel like people may benefit from a 5-minute break, right? It's getting close to lunchtime. I can sense the sort of lack in energy, or maybe I'm just projecting my lowering energy levels onto you, right? But maybe let's take a quick 5-minute break, and we'll come back to less decoding at that point. I see what you mean by the, okay. All right. So let's restart. And now let's talk about one or two tools that will be, so we have like 20 minutes or so, right? 15 minutes. Okay, so at least one tool before lunch, which will be quite useful for proving achievability arguments in the afternoon. So in the afternoon, we'll try to focus on some non-trivial, newer models of ABCs. Well, one older model and then some new models. And for these, one of the basic tools is list decoding. So list decoding is a notion of communication problems which potentially is of interest in itself. As I mentioned in response to a question by Jayaraman Radhakrishnan, that it may be of interest just as a problem of independent interest, that you transmit a message, the decoder should know, well, you said one of these things without knowing exactly which one you said. But really, maybe more interestingly, it's quite useful as a tool en route to proving the more standard sort of results we want to prove, which is unique decoding, right? Because think of it this way, like if you have a tool which can guarantee in a vast variety of scenarios that you can always reduce your uncertainty down to a pretty small set with almost no penalty, you can always do this. And then you can use some extra tools to sort of disambiguate this uncertainty down to a unique element. Then maybe that's a pathway of proving things that is valuable, right? So that will be explicitly the pathway we'll follow for many of our achievability proofs in the afternoon, okay? We'll try to argue as a first step that, oh, Alice and Bob just do list decoding, and then using the same codes, they can actually do a little bit more, and then something will happen, okay? So first, let's understand list decoding, okay? So yeah, as I said, the notion here is basically, no matter what you receive, your uncertainty set should be small. So this is sort of in the usual Hamming ball notion, and in the graph notion, if you're looking at erasure list decoding, your uncertainty set is never too large. There's never more than 3 possible code words given what you receive, okay? Again, this graph is maybe a bad example, but it's too painful to draw a very large graph, right? Okay, so excuse me. So again, remember compatibility, it just basically said x and y are compatible if the number of if xi is yi in all the unerased locations. And we'll say that given any noise parameter p, so if the adversary can erase a fraction p of bits, we'll say a code is list L decodable with list size capital L if for every received vector y, the size of possible compatible code words is no larger than L, okay? This is basically just saying in equations what we already said verbally over here, that no matter what you receive, there's not too many potential confusing things that could have been transmitted, okay? Now, so some observations. So firstly, if you demand L as 1, then that's the same as just unique decoding, right? And in an adversarial setting, this would again be sort of like hard sphere packing, demanding that nothing is confusable, right? So that's maybe too stringent. We saw that really is a very hard problem. Then let's see, the actual code word is, okay, so this is just part of the definition of list decoding. So if there's fewer than NP erasures, then you demand that something like this. Here's another sort of trivial observation that, here the trivial decoder or a trivial list decoder could always output all possible code words, right? And that's not terribly useful. It's not terribly useful to say that the list size is exponential. So really, we want a small list size, as small as possible. And actually, in very general settings, we'll be able to argue that the list size doesn't have to be more than a constant. So again, to return to the question earlier this morning, so yeah, the probability of error could be no more than a half if there are 2 potential things, and indeed you can argue that it will never be larger than it will never be smaller than a certain the probability of success will never be smaller than a certain constant, which you can also prove using list decoding arguments like this, okay? But just to make life easier, so instead of getting down to a constant size, just for today I'll focus on polynomial list sizes. So polynomials are much smaller than exponentials, and I can therefore afford to be a little bit sloppier in my calculations, so I don't have to follow through all the epsilons and deltas. So I'll just focus on polynomial list sizes. keep in mind that you can get down to constant list sizes as well without too much more effort. Okay, and indeed, like there's a lot of recent work in many different settings, theoretical computer science, where these things have concrete applications. Figuring out the constants, figuring out efficient list decodings in the large alphabet setting, in the smaller alphabet setting. It's open, big open question. There's a lot of literature in this work. There's an excellent monograph by Venkat Guruswamy, and other people have been working on it as well. And the theoretical computer science folks really have nice work in this direction. So I'll just give a very high-level exposition just for the specific case of the erasure channel, because it will be useful for the afternoon's talk, and try to give an achievability and try to quickly argue a converse. Okay, so we'll try to argue that under adversarial erasures, where the adversary can erase at most np bits, there are codes which are list decodable at rate c minus epsilon. So where c is 1 minus p. So basically the Shannon capacity of this channel. Okay, so it's list decodable at the Shannon capacity minus epsilon with list size, well, in this case constant, right, order 1 over epsilon. And conversely, so if you demand a list decodable code of rate c plus epsilon, then the list size must be at least exponential, must be at least 2 to the n epsilon. Okay, so this is what a converse for a list decoding would look like, and it's kind of strong. So okay. So here's how an achievability would go. It would say fix a particular. So it's kind of the Shannon, the Shannon argument for proving achievabilities for let's say the capacity is 1 minus p for an erasure channel with random codes. It's sort of similar, except we do a certain concentration inequality step a little bit more carefully. Okay, so let's just look at that. So we choose the rate, we choose the Shannon rate, we choose a rate of 1 minus p minus epsilon, pick a random code, that is for every message we choose a uniformly random code word, right, so binary vector of length n, uniformly at randomly, again just like Shannon's case, right, so it's just a random Shannon code. And again, let's just choose epsilon to be 1 over L, just to be explicit, and so on. Now, what will the bad event be? So in this case, the bad event is not that you cannot decode. The bad event will be that there is at least one potential received sequence y, for which there are at least there are more than L potential transmitted code words, right? That's the bad event that you have to worry about here. So so fix some y. There are at most, let's say, 3 to the n possible y's, right? We'll even take a union bound over all possible y's. So why are there at most 3 to the n? Well, each element can be 0, 1, or erasure, right? So worst case at most 3 to the n, actually less than 3 to the n, but 3 to the n y's. And now let's compute the probability of something like this. So the probability that give like a randomly selected code word for a specific message is compatible with a given y is basically just the volume of the number of x's which match with y in the unerased locations, right? So look at a specific y. Yeah, maybe we should have had a diagram for this, and now I'm going to run into the whatever. Actually, can I request the organizers that over the lunch break we sort of re-clean the thing, because it will be useful, I think. But the argument goes like as follows. So you fixed your y. So this y has no more than np erasures. It's got some erasures like this, right? And therefore it has to have some zeros and ones over here, right? So now for your x to be a bad x, it must be the case that it has to match these locations, and it could be anything over here, right? So the probability of this happening, if my x is uniformly randomly chosen, because that's my codebook design, so the probability of this happening is at most 2 to the minus np, right? Because every bit over here has to, it is, let's do this more carefully, it's at most 2 to the, so each of these has to match, so it's half to the n times 1 minus p, right? Because there are at least this many locations where they have to match, n times 1 minus p, and the probability of matching over there is half to the n minus p, right? So it's like this. So, so now, what is the probability that there are L plus 1 such code words? Well, because the code words have been independently chosen, so you can just take a independence bound, and then it behaves kind of like this, right? So because of this, then you can do sort of a tail bound. You have to be a little bit careful. You can try to use a Chernoff bound, but you really have to use a very carefully tailored Chernoff bound, because in this extreme regime, where the expected value is very small, the deviation is very large, and so on, like the standard Chernoff bound doesn't work. You have to use a carefully tailored version. So instead, I'm just explicitly doing the Chernoff bound, directly. So the probability of something like this is, well, there are at most, there should be 3 to the n, but let's say 3 to the n times, because that's the number of possible y's you could have, times the 2 to the nr choose L plus 1. So this is the number of ways in which you can have 2 to the nr choose L plus 1. Yeah, so of the potential code words, this is the number of ways you can have L plus 1 code words colliding with this, times the probability of a bad event, right? Times, I think, another union bound corresponding to, so this is if there are exactly L plus 1 code words. It could be L plus 2, L plus 3, and so on. Each of those turns out to be a smaller probability than this one. So you take another union bound over the potential number of possible values of the size of the list, okay? But that's still another exponential. I'm going a little bit fast here, but I mean, hopefully it's all believable. It's basically just saying, take union bounds over exponential size sets, like how large is the list size, which is the possible y, and so on. All of these are just exponentials. They all get swallowed up over here, and then you have this is the number of ways in which you can choose the bad code word falling into this, and then this is the probability of having a list of that size over here. Okay, and then you carefully do the math, and it becomes exponentially small. Okay, so so this basically says that if you've chosen your rate at the Shannon rate, then you can get a code of basically matching the Shannon rate, which doesn't guarantee unique decodability, but is not too far away from it. There aren't too many potential confusing things. Okay, now this is a little bit beguiling. You may wish and hope that for any channel this is sort of true, and it's sort of true, but it's not quite true. Okay, so in the afternoon we'll look at examples where there are channels where the list decoding capacity is less than what you might guess the Shannon capacity to be, but then you think about it, then you're like, okay, this is right. So let me just to sort of foreshadow the afternoon a little bit, tell you about the list decoding capacity of a different channel, which is also quite natural, also of interest. So you have the message is encoded to some xn, which is now in Rn. Okay, so it's a vector of length n. It's an Rn intersect and also x. Yeah, let's just write it like this. So also the x vector, the norm of this vector square is less than np. So basically, you can transmit a sequence of real numbers of magnitude at most np. Okay. Then some noise gets added, some s vector gets added. This x vector can depend on this x. This s vector can depend on the x vector. Again, the s vector has a norm constraint. So the norm of the s vector, L2 norm square is less than nn. So this is the amount of noise that can be added. Okay. And then you want to decode based on what you receive over here. Okay, and you want to output a small list. Okay. So this looks like, at first sight, it really does look like the list decoding version of the AWGN channel, right? So you would hope that you could prove a similar result like that over here, right? So you would hope that the capacity, that the rate that you can choose over here, the number of messages that you could choose over here would be half log to the base 2 1 plus p over n, right? 1 plus the power constraint over here divided by the power constraint over here. But this is not true. You can prove indeed that the list decoding capacity in this case is there's a missing 1 over here. So the list decoding capacity is half log p over n. Okay? And the reason for this is because it turns out that in this case, the adversary can behave in a certain manner which will result in a different channel. So there are many different things the adversary can do, but in particular he can behave in a certain manner where this S is equal to some S1 plus S2. This S1 will try to cancel off a little bit of the X. It will try to cancel off some part of the of X. And this S2 will be random noise. Okay? So what ends up happening is that it becomes a different AWGN channel with some different power constraint, a smaller power, but also a smaller noise power. And when you do that optimization, then P prime, then 1 plus P prime over N prime turns out to be equal to P over N. Okay? So verbally, this is like saying that the adversary should sort of cancel out a little bit of what Alice is saying, make her softer, and then use the rest to add some noise. Okay? And this reduces the sort of, this has a strictly smaller Shannon capacity. But what's interesting is that you can actually prove that this is a list decoding capacity for something like this as well. Okay? And this phenomenon is indeed true in larger generality. Okay? So what do I mean by this phenomenon? That given any ABC setting in a fairly large generality, you can look at the possible random channels that the adversary can instantiate. Like for example, in this case, the adversary can instantiate many different possible values of P prime and N prime depending on how he does his power allocation, right? So he can instantiate many different Gaussian-like channels. He chooses the worst random channel to instantiate, and the Shannon capacity of that worst random channel is the list decoding capacity, okay? Which is a very useful rule of thumb because that allows us to say something quite general about many different types of channels, okay? And indeed, you can repeat many of the steps in this proof really using that intuition over there, okay? And there's a very nice paper by Anand Savate which does almost this. There's a few things extra that could be tacked onto that, but this is also known, it's in the literature, okay? All right. So, so this is the achievability. I'm really out of time, aren't I? In fact, I'm over time. 1 minute over time. Let me therefore just spend tell you two more things which will be useful. Firstly, the converse should not be too surprising, so I'll just go over it very quickly. I won't even talk about this converse. This is just a sort of counting argument. But really, the converse follows from, for example, could follow from what's known in the literature as a strong converse for channel coding. So if you try to transmit at too high a rate above the channel capacity, then not only do you have a probability of error bounded away from 0, but in fact your probability of error must go exponentially towards 1. And you can use that to argue that the list size must be large, it must be exponentially large. Or you can directly do a counting argument, an averaging argument, and so on, and you get something. But here's potentially the more interesting thing, which is at least for the erasure channel and so on, and actually potentially for many other channels as well. Not only can you get list decoding with random codes, you can get list decoding with linear codes as well. And that argument is actually quite not too bad. You can layer that on to what we've already said. Okay? So let me just talk about that, and then we'll stop, I promise. So, so basically, now we're going to try to repeat the proof that we did for random codes, but we're going to do it with much more structured codes, linear codes. Now, what's the first and most immediate obstacle when we try to repeat the proof with linear codes? Our code words are no longer independent, right? So if you remember, one of the steps we did in proving list decoding was to say, well, if the first code word is a bad code word, the probability that the next code word is also a bad code word is independent of the first code word, and so on, because the code words in a random code are chosen independently. The code words in a linear code are not chosen independently. They're chosen using a common generator matrix, right? So that independence argument is no longer true. However, any set of a certain size must have a subset of linearly independent code words. This is just a fact of linear codes, right? Someone gives you a set of size S. If it's a binary code, then it must have log S linearly independent code words, right? Just because given a certain dimension space, you can only have 2 to that many code words within that subspace, right? So the basic observation is this. Given a certain set of code words, there must be a subset logarithmically smaller than that set size, which are linearly independent. The next observation is perhaps not surprising for anyone who has studied information theory, coding theory, blah, 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 but linear independence is critically related to statistical independence. So if you have linearly independent code words, or actually linearly independent messages, then you have statistically independent code words. Okay? with a little bit of argument, you can prove this. And therefore, you can repeat basically the same arguments that were done earlier, but now via the subset of messages which are linearly independent, and therefore the corresponding code words which are statistically independent. You can repeat that same argument, and now instead of a list of size 1 over epsilon, you'll get a list of size 2 to the order of 1 over epsilon. Okay? Now this is really just the argument. You can find it in a single paragraph in one paper, a single paragraph somewhere else in some other paper. It's one of those folklore things. Okay? But that one of those papers is this remarkable paper by Guruswami, Hastad, Koparthi, and I'm missing someone, but it's a really nice paper where they spend a considerable amount of more effort getting this 2 to the order 1 over epsilon down to 1 over epsilon again. So at least for certain types of channels, you can actually get essentially the same rates even with linear codes, okay, which is quite remarkable, I think. So you lose basically nothing by linearity. That is, however, it requires, well, firstly, it requires many more arguments. It's not clear how stable that is to other types of ABCs and so on, and something else. But just to say a little bit about that other paper, which I'm not referencing at all except verbally, that other paper uses this new idea called generic chaining, or relatively new, at least in our field, and it's a whole other ball game, which I think is really quite interesting, and it's worth following up on if you're at all interested in these things. Okay? But punchline, list decoding is a useful concept. It allows us to treat adversarial channels almost like random Shannon channels, or at least a certain random Shannon channel, the worst random Shannon channel that the adversary can instantiate. You can use the same codes essentially as Shannon codes. You do have to relax your decoding criterion. It has to be a small list size. And in some cases, you get to use linear codes as well, which is quite nice. You can, and the converses are basically follow through via strong converses from information theory. Okay, and I think that's really all I did want to say over here. In which case, I can let us all go for lunch. Yeah, so that's basically it. All right, any questions? Okay, time for lunch. Sik fan la, as we say in Hong Kong.